There's some properties of vectors with vector addition and scalar multiplication, and most of these are pretty sensible. All right, they just kind of make sense the way that they work. So, for instance, if we had three vectors, u, v, and w, and c and d are scalars, this one basically says that vector addition is commutative. Okay, so if I do it front to back, it doesn't matter, or forward and backward. All right. This one says that vector addition is associative, and also we can distribute. Okay, so if we add the zero vector, it's an identity. If we add the opposite of a vector, it gets the zero vector. This is the associative property of multiplication. This is our distributive property. All right. Um, there should be a plus, by the way, in between here. I'm not sure what happened, but this should be u plus v plus w. So it should be associative there. This is another distributive property. If I multiply by 1, then that's an identity. If I multiply by 0, I get the 0 vector. And if I take the magnitude of a scalar times the vector, that means I could just take the absolute value of whatever that scalar is and multiply by the vector. Okay, all of these are actually really easy to prove in 2 dimensions. We're not going to prove any of these, but most of them make sense to a lot of students. So we're not going to spend a lot of time actually doing any of these. We're just basically going to see them as we go along. All right, so we have these unit vectors, and we just want to make sure we understand what a unit vector is. And a unit vector is basically a vector of magnitude 1, and it's either in the x direction or the y direction. All right, so if I were to draw these on a Cartesian plane, all right, just kind of seeing what these look like, the vector I, if this is going to be the point 1 comma 0, okay, this would be the unit vector I. Right? And then if I went up to the point 0 comma 1, okay, this would be the vector j. And those are the unit vectors, okay? So the unit vectors are vectors of magnitude 1 solely in the x direction and solely in the y direction, right? We can use those to be able to write vectors in a linear combination. And so if I know the component form, okay, which we've looked at already, then what I could do is I could just stick a u, or we could stick an I and a j in front of those. Okay, so these are actually really easy to work with. Okay, so if I have a vector in the component form -3, 4, and let's say I want to call that u, u would be equal to -3i plus 4j. Okay, so that's literally all you have to do with vectors to write them from the component form into a linear combination. Okay. If I had this vector, which I'll call u, that would be 2i plus 0j, or another way to write that is because 0 times the j would be a 0, is that u would be equal to 2i. And then finally, if I had this, where I had the component form as 0, -7, I would have 0i plus 7j. This would cancel out, and I would be left with our vector u is equal to 7j. Okay? All right, so really easy for us to be able to perform these operations as a linear combination. And you might be thinking, well, why do we want to do that? All right, well, it's just a different way of being able to write these vectors. Okay, in engineering, we use this quite frequently. In pure mathematics, we try to use this form a little bit more often just because it's a little bit easier. So just get used to both of these as we're going to use them interchangeably. We could do the exact same thing as we did before, vector addition and vector multiplication, scalar multiplication. So if we have u is 3i plus 2j and v is 6i minus 5j, u minus v. So what I would do is I would add the I components together. Okay, so this would be if I had 3i plus 2j, and to that I wanted to add 6i minus 5j. All right, let's put a little carets over top of those. And so what I would do is I would add the I components, so it's just like terms. Okay, so this would be 9i, and then we have 2 minus 5 in the j, so it would be minus 3j. All right, so that's literally as easy as it gets. Okay, so just like terms. If I had 4v minus 2u, then what I would do is I would start by multiplying. So I have 4 times 6i minus 5j, and then minus 2 times the quantity of 3i plus 2j. And so if I distributed, I would get 24i minus 20j, and then minus 6i plus 4j. And so if I combine the I components, 24 minus 6 is 18i. Negative 20 minus 4j is a negative 24j. 2u plus 3v, we would have 2 times the quantity of u, which is 3i plus 2j, plus 3 times the quantity of v, which is 6i minus 5j. If we distribute through, 2 times 3 is 6, 2 times 2 is 4. Okay, so we get 6i plus 4j, 3 times 6, 18i, 3 times negative 5, negative 15j. All right, and so when we combine 6 and 18, 24i, 4 minus 15, negative 11j. All right, so that's how easy it is. Okay. Finally, a magnitude problem. Okay, not too difficult. So 3u, so I'm going to have 3 times the quantity of u, which was 3i plus 2j, and then minus 2 times the quantity of, we had 6i minus 5j. We're going to distribute. Now I'm ignoring the magnitude for a moment. Okay, I'll show you what to do after that. So we're going to distribute. All right, and so we're going to get 9i plus 6j minus 12i minus 10j. And so combining like terms, okay, or combining i's, this becomes a negative 3i. And then we have 6 minus a minus 10, so that becomes plus 16j. Now we have to find the magnitude of that. So to find the magnitude of negative 3i plus 16j, then all we're going to do is we're just going to take those components and square each of them under the square root. So that's going to be negative 3 square plus 16 square. And we just type that into our calculators. Okay, so we would end up, now we're not going to approximate it, we'll get an exact value out of this. So we would get square root of 3 square. And it's technically negative 3 square, so we just type it in like that. So negative 3 square plus 16 square. All right, that doesn't give us an exact number, unfortunately. Okay, so what we're going to do is let's just pull this out. Okay, and it gives us 265. All right, we might have to go through and see if we can simplify that. Okay, so let me write it like square root of 265. Right. And what we're going to do is let's divide by perfect squares. Okay, so you might remember that trick that we looked at before. So 265 divided by 4. It's not a perfect square because this is not a factor. So I'm just going to keep dividing 265 by my perfect squares just to see if I have a factor of perfect squares. Okay, so 265 divided by 9, that doesn't work. 265 divided by 16, that doesn't work. So again, as long as you keep getting decimal values, that means it's not necessarily evenly divisible. Okay, 265 divided by 25 doesn't work. 265 divided by 36 doesn't work. 265 divided by 49 doesn't work. 265 divided by 64 doesn't work. 265 divided by 81. All right, and now we're starting to get close to where we know it's not going to work. Once this number gets below 1, then we know it's not going to work for anything. Okay, so divided by 100. Nope, that doesn't work. 265 divided by 121. 265 divided by 144. 265 divided by 169. All right, and these are all perfect squares. So we can kind of stop. Okay, it's not going to work out. 196, 265 divided by 225. And then finally 265 divided by the next perfect square up would be 16 squared, which is 256. All right. And so the next one up from that would be 289. All right. So it doesn't work out. Okay. So I had to do that just because we need to see if it's simplified any further. All right. Occasionally you get like these nasty ones like this where you just have to go through a whole bunch of them. Okay. So that's just a reminder of how to simplify, if you can, something like this. Okay. But now we know how to put vectors into the component form. Okay. So that's what we did before. We wrote them as a linear combination. So now we know the component form, we know the linear combination, and now we remember how to do operations on these things, okay? So our next video, what we're going to do is we're going to take a look at unit vectors in specific directions from regular vectors.